This webinar is sponsored by NEC Corporation, a $37 billion technology leader with over 100 years of innovation. Their ProgrammableFlow Network Suite was the first commercially available enterprise-class SDN solution to leverage the OpenFlow protocol. Thank you for your time and interest in NEC's ProgrammableFlow Network Suite.
This sponsored webinar is one of many IP-Space Data Center webinars. You can register for live sessions, buy the recordings, or get access to all of them with a yearly subscription. For more information, visit ipspace.net/dc. The whole OpenFlow network, and in our case, the ProgrammableFlow network fabric, appears as a single device to the outside world. So from the outside, it looks like a single switch with many ports, and we don't really care what's inside. All the forwarding behavior of this cloud that we can't see yet is controlled by the OpenFlow controller. In our case, this is the ProgrammableFlow controller from NEC. And anyone looking at this picture would quickly say, hey, but isn't the controller a single point of failure? And actually it is. And you know what you have to do when you have a single point of failure. You add another one. The same thing NEC did, and so in every resilient ProgrammableFlow network, you should have two controllers in a cluster. The cluster between them is established based on your configuration, more or less automatically. And once they work in a cluster, they constantly exchange data so that if one of them fails, the other one has all the information it needs to take over and continue managing the network. And like with any cluster, you need some sort of connectivity between the two controllers. And that's the role of the cluster interconnect network between the two. And to make it fully redundant, the ProgrammableFlow controllers, which are actually appliances running ProgrammableFlow software, have numerous Ethernet ports to satisfy all the connectivity needs, among them two dedicated cluster interconnect ports that you use to connect the two flow controllers together, so that you always have two paths between them and a single link failure doesn't cause a split brain scenario. Now, going slightly deeper into the topology of the network, we build the actual physical network with OpenFlow enabled switches. There are some vendors that do switches that can only do OpenFlow. In NEC's case, the OpenFlow enabled switches can work independently, or they can be controlled from the central OpenFlow controller, which is the use case that we're interested in today. So you take a number of these switches, and the first thing you have to do is you have to connect them to the controllers, which is the role of the special OpenFlow control network. So you need additional traditional layer 2 switches to build the control plane network, and you have 2 ports on each controller and 2 ports on each OpenFlow switch, so that you can build 2 separate OpenFlow control plane networks, and actually you have an air gap between them, so if one of them fails, the other one will still be operational. A question from the audience based on the previous slide: if there are only 2 ports for cluster interconnect, how do you ensure high availability for network spanning multiple sites? I wouldn't use ProgrammableFlow for an OpenFlow network that would span multiple sites. I would have one set of controllers on one site and one set of controller on the other side, and then use traditional mechanisms to connect them together. Because remember, if you build a distributed OpenFlow network, then one data center depends totally on the availability of the controller in the other data center. If the links between the data centers go down, you lose one data center, not just the links. Next question: what about the latency of communication between the controller and the switches, and/or the time required for the controller to figure out the forwarding tables?
Yeah, the latency is essentially only comes into play when you're trying to push a forwarding table entry into the switch. But as you know, the reactive nature of it is that that delay just adds to the time to set up the flow. In the meantime, the packets are essentially still getting routed through the controller. So we don't have any sort of gap or missing forwarding point in this thing. But yes, it is true that the latency between the controller and the switch is important, and that's why typically they're in the same network. It's not like a controller you would place far away in the WAN.
The next related question is, why do we need the control plane network? So why do we need these extra switches? The problem is that if you program the OpenFlow switches through in-band means, then you can cut yourself off from the network. So it's safer to have totally separate control plane network than to try to program the switches through in-band communication. And by the way, keep in mind that this is a solution that was targeted primarily at data centers. You can assume that these switches are relatively close together and that it's not a problem to build a separate control plane network. Okay, and then we have the data network that is used to forward the user traffic. And this data network is fully controlled through the OpenFlow entries downloaded from the controller into the switches. And finally, there is the fourth network, the management network, which the programmable flow controllers use to communicate with the outside world. In the ideal case, you would actually build 4 separate networks for resiliency purposes. If you want to be on the cheap, of course, you can combine the management and the control plane network, but maybe you should keep all 4 of them separate. Now, you can build any topology you wish with the programmable flow switches, and the controller will figure out what the topology is. So you can build a ring, you can build a full mesh, you can build whatever you wish. But as it's always the case, it's optimal if you use a cloth or leaf and spine fabric to build larger fabrics. Because with that, first, you get equidistant bandwidth between all endpoints. And secondly, you have the ability to keep the complexity on the network edge and use high-speed, simple switches in the network core. Not surprisingly, NEC has 2 models of programmable flow OpenFlow switches, and one of them is primarily used in edge with gig ports toward servers or external devices and 10 gig uplinks. And this one has loads of OpenFlow, so the 7 or 10 tuple entries that you can use for fine granular packet matching or policy-based routing or what have you. And the core switch has 10 gig and 40 gig ports, but it only has 750 full OpenFlow entries, but you don't need them in the core. You only need layer 2 or something similar to pass the traffic between the edges. And recently, there's a third switch, and it's a virtual switch for Hyper-V. And this virtual switch is actually, as far as I'm aware, the first shipping third-party switch for the new Hyper-V environment, fully OpenFlow capable with lots and lots of flow entries, but that's easy to do because this is all done in software. And it supports over 1,000 virtual ports, so this would be the VMs, and 8 physical ports. So with the PF1000, you can actually extend the OpenFlow down into the hypervisors. And what this gives you is that the whole network, the physical switches and all the hypervisors, appear to the outside world as a single control plane, as a single management interface, and as a single device that you have to configure. And with that, you can then configure consistent end-to-end connectivity, and you can enforce the virtual networks, because the programmable flow controllers control everything from a VM on one end to a VM on the other end. Now, I already mentioned that the OpenFlow controller can figure out whatever topology you're using in your network. And now let's see how that's done. Initially, the programmable flow controller has no idea what's going on. When the devices start connecting to the programmable flow controller, the controller starts building the model of the physical topology. So for every device, it adds a node in the model. But it still doesn't know how these devices are connected to each other. What happens next is there are special OpenFlow messages that the controller can use to figure out the ports on the device and the port status on the device. So the controller goes through the interface discovery portion of the process with every single switch or router and figures out how many ports that switch has. But it still doesn't know how those ports are connected to other switches. To figure that out, the programmable flow controller uses the same mechanism as routers or switches do in a regular network. It uses protocol to discover topology. Only in this case, the individual switches cannot do anything on their own because the control plane is in the controller. So this is the only place that has some intelligence. The controller has to tell individual switches that they have to send out packets to other switches. So for example, the controller would tell this switch to send out an LLDP packet over this port. There's a packet out OpenFlow message, and in the packet out you specify which packet you want to send out through which port, and an LLDP packet is sent out through this particular port. And this other switch receives the LLDP packet, has no idea what to do with it because it has no local intelligence. All the control planes running here, don't forget that. And so the switch sends the packet through packet in message back to the controller. And now the controller can say, okay, I've sent this message out through one particular port, and it has been received through this other port on this other switch. So these two ports must be connected. And so it eventually builds the topology of the network. Now that we have the topology and we know where individual endpoints are, which we can learn through listening to, let's say, their broadcasts if we're talking about layer 2, we have to do some routing functionality. Let's say A is sending packets to B, and this first switch has no idea what to do with the packet, so you know what it will do. It will send a packet in message to the controller, telling the controller, I've received this and I really have no idea what to do. The controller would look at the topology of the network, figure out how to get to B. By the way, it will also update the MAC address table, so it knows where A is now. It will update its ARP tables, it will update its IP tables, and it will calculate the best path across the network. Now, this best path could be least cost path, or it could include some policy map. And the policy map tells you how to use various equal cost paths. So you might want to use one path for certain traffic and some other path for some other traffic. With that, you actually achieve policy-based routing. But you see, the point is that in traditional networks, you had to do policy-based routing on every single device. And here, you only configure it in the controller, and the controller takes care of all the rest. So the controller got the packet, it knows where B is, it figures out what the best path is, and now the controller downloads the flows to all the switches. So to go from A to B, this is how you have to go. And OpenFlow entries are obviously installed along the best path. Sometimes the controller might be able to pre-install the backup path as well. But sometimes that just doesn't work. For example, if this link over here fails, there is no way that a backup path could be pre-installed here because this switch cannot react to a link failure over here. What the controller has to do at that time is, after the link failure is encountered, it recomputes the topology and installs alternate flows into all the switches along the path. If you have questions after watching this video, send a tweet to @iOSHint or send me an email using contact form on ibspace.net, where you'll also find information about other data center webinars. For all commercial questions and programmable flow evaluation requests, please contact NEC.